Okay, there should be plenty of questions today. So who wants to start?
Sir?
Yeah, go ahead.
Yeah. Could you please explain, the working of the triplet
Abhishek,
circuit?
can you please upload the lecture slide I have, as far as I know? Could you just check? I think I have. Yesterday, or maybe today, yesterday night or today morning. Yeah, sorry. Could you just repeat that?
Yeah. Could you just explain the working of the triplet circuit?
Do
Voltage
you
triplet.
understand the doubler circuit?
Yes, sir.
The tripler should be straightforward. Then I don't need to explain it.
I intuitively understand, I can get the voltages by applying KVLs.
Hmm.
Yeah, but could you
Yeah, that's
explain it?
not intuitive. Intuitively understanding is you should be able to sort of figure out where what is storing the voltage where and why is it happening. That I think I will leave you to worry about.
Okay, sir.
I don't want to take the fun away.
Okay, sir.
Okay. It's actually quite interesting. If you understand the doubler circuit thoroughly, in fact, I have explained the doubler behavior pretty well, I guess. I hope. So if you understand that properly, you should be able to figure out the tripler. Just notice where the voltages are being taken. That's the voltages are not all with respect to the ground. So just those voltages which are marked in the circuit.
Okay, sir.
Think about it. It's actually a nice, interesting problem to think about. Okay, next. Anything which is not as exotic as a tripler, something which might be useful for, say, the exam which is coming. Come on, when is the exam? Monday or Tuesday? I don't remember.
Tuesday.
Tuesday. So you have an exam on Tuesday, and nobody has any questions about the topics in the exam?
Sir,
Yeah.
sir, can you please discuss how to calculate power from the complex?
Okay, I've done that once, but let me, maybe I will do it again. Not a problem. Okay, so the basic idea is this. First of all, you do not calculate power from the complex version. That's the first lesson. You cannot. Why? Because the whole idea of using complex exponentials work on the basis of linearity. Okay, so for all linear operations, do the thing with complex numbers. In the end, take the real part. It will work out. But for power, if you use the complex number, so v0 e to the power. So when you say v0 theta, this actually, okay, this is where things get a bit tricky. When people use the angle representation, then this voltage is always, what is quoted here, is actually the RMS voltage. Okay. The corresponding complex number version is actually v0 by root 2 to the j theta. Of course, there's an e to the j omega t. This is the complex number version. Okay, let me just, for the time being, I will put a tilde on top of the complex number version just to distinguish it from the real number version. Okay? Is it okay? So actually, the voltage as a function of time is going to be v0 by root 2 cosine omega t plus theta. At this stage, let me warn you that when I discussed this earlier, so those of you who remember the earlier discussion, you might see something different here because now you have v0 by root 2 instead of v0. That's simply because this v0 that we are quoting here is the RMS value. Sorry, I have made a mistake. Can anybody tell me what mistake I have made?
It should be root 2 should be multiplied with V0.
Yeah, it should be root 2 times v0, of course. If RMS is v0, there's a peak value or the amplitude is V0 root 2. So that's what you really should have. Root 2 V0. Okay. So this root 2 factor may or may not be there depending on whether you are actually quoting it this way, that is RMS value and the phase angle, or if somebody says it is V0 cos omega t plus theta, then that's what it is. Then you don't have a root 2. Okay. So I of t would be root 2 I0. Same. I0 is the RMS value now, not the amplitude. Cosine of omega t plus phi. And in the complex version, I tilde is actually I0 root 2. It's about J phi. And there's an e to the j omega t. Okay. Now, these are the actual voltages and actual currents, instantaneous values, the correct values. And these are the ones you should use to calculate power. Now the power calculation is straightforward, right? You just multiply these two. And so you get the instantaneous power this way. But of course, this instantaneous power is rather rapidly fluctuating. In fact, if theta were exactly equal to phi, this would have a cosine square omega t plus theta, in which case you would get a fluctuation which is twice the frequency of omega. So what we are usually worried about is the average power which is averaged over a complete cycle. That is, you integrate pt dt from 0 to 1 complete time period, that's 2 pi by omega, and divide by the time period. That gives you the average power over a complete cycle. And since this is periodic, well, if you were to calculate this for one cycle, you will get this value. If you calculate for 1,000 cycles, you will again get the same value. It's just this will become 1,000 times bigger, the upper limit, but because of the periodicity, the integral will be 1,000 times bigger. You are going to divide by 1,000 t, so that will just cancel. So this is a nice thing to talk about, the average power. And if you calculate that, you are going to get V naught I naught cosine of theta minus phi. Okay, this is what you are going to get. End of story. Okay. So what should you really do? This is your actual value. Now you can always say every time you calculate power, you give up on the complex numbers, you take the real functions, calculate with that. That's a perfectly legitimate thing to do. It's just that it's a bit of a shame to give up on the complex numbers which work so well for us. And we might try to figure out a way of handling this with the complex numbers. Now, the complex numbers, if you use e to the power j theta for the voltage and current as complex current as e to the j phi, of course, that's an e to the j omega t. Notice that if you were to multiply this complex voltage and by the complex currents conjugate is important because that will do two things. First of all, that will cancel out the e to the j omega t between the two, because one will be e to the minus j omega t, the other will be plus e to the j omega t, and it will make this phase angle theta minus phi. So this, of course, is still a complex number. This is not the power. But notice that if you take the real part of this, you get exactly this. Okay? So this is actually cheating. The point is the complex versions worked fine as long as we were doing linear operations. With nonlinear operations like where you multiply by a voltage by a current, in the case of calculation of power, that method will not really work. You should work with real functions, cosines, and so on. But the answer, after you calculate the whole thing properly, you see that the answer comes out to be this. Provided, of course, V0 and I0 are the RMS values. If the V0, I0 were peak values, there would be a by 2. Okay. So the only difference in the formula would be if you had if your voltage current were quoted using peak values, You would have an extra half. If it's quoted using RMS values, you don't have an extra half. That's it. Okay. So then the point is, instead of giving up on the complex voltage and current, what you can always do is use this formula, which gives you the same result. So this is a trick. Using the complex voltage, in any case, you remember that using the complex voltage and complex current was always a trick. The real actual voltage and current are not complex numbers, right? But the trick here works despite the non-linearity, but for that you have to be a bit careful. You have to take the complex conjugate of I multiplied by V, or by the way, it works the other way around as well. You could take the complex conjugate of V multiplied by I and take the real part. But complex conjugate of one of them with the other, of course, these two quantities are actually complex conjugates of each other. So the real part are just the same. Does this make sense? Yes?
Yes, sir.
So basically, for example, if somebody gave you this as voltage and this as current, it's here too. Then V0, then Vi star would actually be V0 I0. Now, remember, whenever you are giving it this way, you actually mean the RMS value. So angle theta 1 minus theta 2. That's a product. Of course, this really means that the real part is going to be V0 I0 cosine of theta 1 minus theta. Exactly whatever this formula says. You're just recovering that formula using complex number. That's it. Okay. Next question.
Sir, can you go to the previous page? Once.
Yeah, can, I guess. Yeah, where
Sir,
do you want me to start?
sir, at last, where you're writing at last. Sir,
This
here
thing.
it won't be divided by 2.
Whether it will be divided by 2 or not, that's your question, right? You're cutting off, so I'm trying to assume that what you're saying.
Sorry, into 2 it will.
No,
Uh,
look, it will not be into 2 simply because when you do the power calculation, these 2 cancels out. Okay. Remember, twice cos omega t plus theta into cos omega t plus phi. That actually gives you a cosine and another cosine. Sum of two cos A, cos B, right?
okay.
That gives you cos of A plus B and cos of A minus B. Cos of A plus B is an oscillatory function. It just cancels out. Cos of A minus B is actually independent of t because the omega t cancels. The oscillatory function gives averages to 0. Okay, the other part averages to cosine of theta minus phi because the other part is constant at cos theta minus phi. So 2 actually cancels out. Okay, so this 2 is there only because this V0, this I0 is the RMS. If they were the RMS, then this 2 would cancel out and you would get exactly V0, I0. If this V0 and I0 instead of being RMS were actual peak values, then there would be a by 2. Okay. So you have to be a bit careful. You have to rely on what exactly is being given. Are you being quoted RMS values or are you being quoted other values? Okay. Is that clear now? So
Yes, sir.
for RMS, you don't have a half. For peak, you do have a half. Next.
Yes, sir.
No, I was looking for the next question. Okay, if nobody has a question, then I will go back and discuss something which, at least from your homework assignments, it seems many people have got this one wrong. I'm not going to work the whole thing out for you, although I have already given you the solution as far as I remember. But it seems that either, well, many people making the same mistake can mean one of two things. One is, of course, you have collaborated, which is fine, as I said. As long as you understand what you are doing, then it's fine. But if you have collaborated and made a mistake and nobody has caught on to that mistake, then either you have just copied without thinking, or the real problem is you have thought that you have understood, but you have not. So let me just give you the benefit of the doubt and assume that you have tried to think and got it wrong. Even perhaps independently got it wrong, which is a bit hard to believe. But this was basically the problem. Okay, I will just use the numbers as well, although I'm not really bothered about the calculations so much. So and let me remind you once again, despite the fact that all these resistances are in ohms, frankly, in an electronic circuit, almost invariably resistances will be kilo ohms. So as far as I remember, this was a Thevenin equivalent problem, or at least some problem where you were supposed to use a Thevenin equivalent. And basically, you have a current controlled current source which has a value 1.2 Ix, where Ix is this current. And what we did was, let me just do one. Oops, this is not what I wanted to do. Let me save it. Okay, and then so the one major problem which seems to be confusing quite a lot of you is how much is what exactly does the current source do? A current source produces a current, and the value which is rated there is the current through the current source. It does not add that much current. So what some people have done wrong is you have calculated the result without this current source, and then you have added the current which is 1.2 Ix. That's not how it works. The current here in this line is 1.2 times Ix always. It's not an additional current. There's a current controlled current source. Whatever current you have here, 1.2 times that will be here. Okay? That's what it's supposed to mean, number one. Number two is this. Okay, let me just try to figure it out a bit in a way. Say this is there are two loops here, I1 and I2. This loop, I3 was a loop here. There was some resistance here. So if you wanted to solve it using KVL, you would have made a third loop. But right now, you don't have a third loop. This is not a loop, right? It doesn't close. So you have only two loops here. So what are the equations that you can write down? So for which one of the loops can you write down a full-fledged equation for the KVL? For the first loop or the second loop, or for both? Okay. There are several questions here. In fact, two different questions. For which of the two loops The question number 1 and question number 2, of course, options are loop 1, loop 2 for both of them. These are the options. Loop 1 meaning the one where I marked a current of I1 and so on. So what would you say? Question number 1.
Loop 2.
Question
So
number 1.
KVL works on both loops, but it would be useful to use it on loop 2.
Great. That's the perfect answer. KVL has to work everywhere for the simple reason that Kirchhoff's voltage law is nothing but the law of energy conservation. It has to work. Of course, there may be situations where it appears not to work, but that's because there are some other parts of your circuit which is leaking energy somehow. Not in a standard electrical circuit like this. So the answer is it works for L1, works for L2. But the second part of the answer, second question is actually more useful right now, more important right now. For which of them is it useful? The answer is this loop, the loop 2. But what is important is to understand why is it not useful for L1. And please go ahead, tell us why it's not important.
So in loop 1, there is a controlled current source. So the I1 that we have mapped should not be the same everywhere. So due to this current source, there should be a change or a jump in the current.
Jump in the current. No, I don't really think that's the right thing.
We don't know actually the potential drop across it, like how it would
Yeah,
be.
this answer is actually perfect. The current controlled current source, just like any current source. Okay, the real point is a voltage source, if it's ideal, can drive any amount of current without changing the voltage across its two ends. So the amount of current driven through the voltage source is if it's ideal, is not known at all. It's controlled, it's not arbitrary, it's controlled by external circuitry, whatever is connected to it. That controls how much current goes through it. So if you connect a 1 ohm resistance across a 1 volt battery, which you definitely should never do in real life, you would get a 1 ampere current. If you connected a 10 ohm resistance, you would get a 100 milliampere current. A 1 kilo ohm, you would get a 1 milliampere current. If the battery were really ideal in all circumstances, the voltage across it would stay 1 volt. The current through it can change depending on what you connect to it. For the current source, exactly the same thing happens. If a current source is 1 ampere rated and it's ideal, then if you connect a 1 kilo ohm across it, it will give you a 1 volt. If you connect a 2 kilo ohms across it, it would give you 2 volts. 100 kilo ohms, 100 volts. Well, in the ideal case, of course, in reality, what happens is that you don't have an ideal current source really. You have a current source with a parallel admittance. And so if you connect a huge resistance across it, the output voltage tries to rise a lot, but that will make the current also flow, a sizable current to flow through the internal admittance of the source, which would mean that that amount of current will get lost. It will not go to the outside. So that's why the current source will actually, current going out will actually drop. That's for the real situation. But for an ideal situation, the current and the voltage drop across a current source is completely arbitrary. Could be anything. Okay. And that is why you cannot write the KVL equation down. You can, of course, write the KVL equation down by saying, okay, there's a voltage drop here. Some V. But I don't know what that V is, so it will not help. Okay. Clear? And the major mistake which many people have done is people have calculated, what you need is this voltage drop, right? If you're calculating the Thevenin voltage, you need the voltage drop between these 2 points which are marked, this one and this one. Okay, that's what you need. But what many people have done is that you've calculated the voltage drop between these 2 points and quoted that as a Thevenin voltage. Why is that wrong? I'm telling you that's wrong, but why is it wrong?
So because of the current source.
Because of the voltage drop across the current source, right? Note that there's also between this point and this point, if you compare these 2 points where you actually want the voltage drop and these 2 points where you have calculated the voltage drop, there are 2 things. There's this resistance, there's also this voltage source. This resistance is floating, it carries no current, so there will be no voltage drop across it. For resistance, Ohm's law is supreme. If there's no current across it through a resistance, there's no voltage drop across it. Okay, but for a current source, the voltage drop is something which is not really that easy to calculate. Okay, or it can be calculated, but not that straightforward, not in that straightforward a manner, not directly. But this voltage is not equal to this voltage. That's the important part. The voltage that you really need, the VThevenin, is not the voltage drop across this. So you have to remember a current source can, because it's a current source doesn't mean that the voltage drop across it is 0, because the voltage drop across it can be arbitrary. So how would you find the voltage between this? What you would do is go from here like this. And that will give you the voltage difference, right? Find the voltage drop, voltage rise here, 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 and you're done. Add them together. Is it okay? Now, how would you actually calculate it? Okay, let me just put in some values here. I don't remember what this voltage source was. Let's say 4 volts. I'm just making this up. Might have been something else. Okay, so as was already pointed out, you can write down this KVL equation perfectly well for this particular loop. And you get 4 plus 5, 9 plus 3, 12 I2 minus 4 I1 equals 4 volts. Okay, I shouldn't really write volts because then I would have to tag in with the ohms. I'm assuming the currents are in amperes. So I don't have to worry about the units any longer. So that's one equation. That's the only loop equation that I can really write down. Okay. Then what do I do? I need at least one more equation to work, right? Okay, how much is Ix, by the way? Can anybody tell me that? Okay, somebody is.
Sir, I2 minus
Ix is
I1.
I2 minus I1. Yeah, right. The trouble with typing it out on the chat box is very often I miss it. Anyway, I could see it this time. It's I2 minus I1. But then, how would you proceed? How would you find out the relationship without any other equation? I have I1 and I2 as my unknowns. Right? If I knew I1 and I2, I could easily find out the voltage changes between this. Then I would be done. How do I find out? 2 unknowns.
The current through 5 ohm is I2, and we can say that I2 equals 0.2 Ix using KCL.
I2 equals 0.2 Ix. How do you say that? Okay, let's see. How would you say that?
Because at one of the nodes, Ix is entering and 1.2 Ix is leaving, so the other branch must contribute the other.
Okay, that would be a good way. Good, that's a good way. What you're looking at is you're applying KCL here. You're saying Ix is going in, 1.2 is going out. That would mean what? You're slightly off. This would be 0.2 Ix, right?
Yes, sir.
So I2 is not 0.2 Ix, I2 is minus 0.2 Ix.
Yes.
Okay? Does that make sense? Okay?
Yes, sir. Yes, it's in the opposite.
But yeah, but fine. But how that still? So I2 Ix is minus 0.2. This is actually very important because If you get that wrong, everything will go wrong. And there's a more direct way of getting that. Okay, this is fine. But can anybody tell me from this loop, how much is I1?
Minus
I already said that I
1.2x.
don't. Yeah. Isn't it? This is I1. The current through every part here. What is the current through this one? There's only I1 here, no other loop current, right? So it's I1 going this way. So I1 has to be minus 1.2ix. Is that okay? Both of these are actually the same result, by the way. Ix is minus 0.2 I2 and I1 is minus 1.2 Ix are exactly the same thing, given that Ix is I2 minus I1. But I would say, in the spirit of using Kirchhoff's voltage laws, or in the spirit of using the mesh equations, it's actually easier to figure this out directly. You don't have to look at a node and apply KCL to that. All you have to do is say, okay, in this loop, the current is I1, and that's it. Has to be minus 1.2 Ix. I'm not saying that the other thing is wrong. All I'm saying is this one should be more natural to think about. So now that you have I1 equals minus 1.2 Ix, and from that, using this, you can easily find out I2, the relationship between Ix and I2. Now you're done. You can just put this in, find out I1, I2. Okay. The actual calculation is, of course, important, but what is much more important is understanding these basic issues. A current source does not add further current. The current source, whatever rating it shows, that's the current it maintains across it. That's number one. Number two, the current source can have an arbitrary amount of voltage across it. When I say arbitrary, that of course is not really true. Arbitrary simply means that the current source does not dictate how much voltage will be across it. That will be dictated by what is connected to the current source. Okay? Right? And the important point is you do not ignore the voltage drop across a current source because it's a current source. Current sources can carry arbitrary voltage or can carry any voltage within reasonable amounts depending on the other circuitry. It's not controlled by the current source itself. That's the important thing. Okay. Any questions about this? Well, it seems that either there is a lack of thought behind everybody, or not everybody, but quite a lot of you getting this wrong, or there's a genuine confusion. So if this is still confusing, ask me.
Hello, sir. Sir, I have a doubt.
Yeah.
So the way I was thinking is that 1.2 Ix, that current control source, is an ideal source. So it does not have any internal resistance. So why is there a voltage drop across
Not true. Not true at all. First of all,
ideal.
this internal, first of all, okay, let me just point out that the only real problem here is that you are not that familiar with current sources. You are more familiar with voltage sources, right? Right? That's why perhaps you don't understand. It's understandable. People don't really deal with current sources that much in early schooling. So let's ask you this. Suppose you have a 12-volt voltage source. If it's ideal, what is the internal resistance of that?
Nothing. Zero.
Nothing. How much current do you think the 12-volt supply will deliver?
Okay. This depends on the circuit, outer circuit.
Okay. Look, ohms, the trouble is you're trying to, even when you were using this for the current source thing, you were using Ohm's law at the back of your mind. But Ohm's law is for a resistance, not for a power supply. In fact, when you say a non-ideal voltage source is a battery, For a non-ideal voltage source, you have a battery in an ideal source in series with a resistance. You don't apply Ohm's law for the whole thing. You apply Ohm's law only to this effective resistance. So you have a voltage rise of E between these 2 points. And if the current is I, you have a drop of IR between these 2 points. So the voltage that you get is E minus IR. Right? You don't use Ohm's law throughout. For sources, Ohm's law doesn't work. And that's not a surprise. Ohm's law works only for resistance, not for other things. The zero impedance of the ideal source really tells you that you can just think of this as a source with no internal resistance, which means no matter how much current you draw, the voltage will not change. In reality, if you draw more current, the voltage will drop. And that's because of this. Similarly, when you're talking about a current source, the reason why you think of a current source I as something which has an admittance in parallel to it. First of all, ideally the admittance should be 0. Okay. What that means is you just have a current source. Does it have a resistance? Does it have a resistance? The answer is that's a meaningless question. A current source doesn't have a resistance. The concept of resistance doesn't even arise here. Okay. An ideal current source for that, just like for an ideal voltage source, it has no internal impedance. That means it does not have any series resistance connected to it. An ideal current source has no admittance. That means it has no parallel admittance line. But you don't go and apply Ohm's law to this part, just like you don't go and apply Ohm's law to this part. That's a different element. You don't go and apply Ohm's law everywhere. You apply Ohm's law only to resistances. And the other thing is, if you have capacitance and inductance, and you're talking of steady state currents which are pure sinusoids, then because the voltage drop across them becomes proportional to the current in the complex number version, that's why you say that they have effective impedance of 1 by j omega c and j omega l. And you have to remember that these two only work for steady state behavior where you have pure sinusoids. If you don't have pure sinusoids, of course, you cannot just feed a capacitance as like a resistance with an imaginary value. You can't. It doesn't work that way. Okay, this just happens because, say, LDI dt for a purely complex current with an exponential current would give you a j omega times L times whatever the current is. But this works only if I is I0 into the j omega t plus phi is inside the I0, let's say. Only then does this work, right? And that only describes a pure sinusoidal current. So if you have a square wave input, you cannot say you're going to use j omega L. What you can of course do is divide up the square wave input, or think of the square wave input as sum of lots of sinusoids. For each one of them you can use. But with different omegas, of course. Okay, somebody was trying to ask something. Yes? Okay, so if there are no further questions, I don't really want to teach you something new today, this being the last day before the exam. So if you have a question, please ask. Otherwise, we will just fold it up. It seems nobody has any questions. Then best of luck for the exam. It will be on Wheeler, and yeah. Syllabus for medicine. I think you are you a BSMS or an IPHD?
Sir, an IPHD student.
Okay, so that's why the syllabus is whatever was taught until this day. In fact, until the day before the exam. But since I have promised that I will not add anything new, so lectures 1 to 12. And whatever was discussed in the discussion classes. Everything. You are allowed to use calculators, you are allowed to use computer programs if you want, but I will not give you computer programming questions in the exam. But if you feel that you want to do a calculation where you need to write a program, fine, I have no problems. And it's of course an open book exam. As long as you don't discuss among yourselves, it's fine. It will be time limited, the way the quiz was. And please keep a scanning thing handy. You will get at most 15 minutes after the end of the exam to upload the scan thing. And last time I did not change the settings simply because last time the settings was such that it allowed less submissions. But in the exam, there will be no less submissions. So you will have questions. Okay, basically you will have questions to answer, which you will have to answer in the question itself. There will be text boxes. Those will be short type, but the entire working, and then in this case now the entire working is proper entire working because that's your answer script. That has to be uploaded within 15 minutes of end of exam, and there of course you will get no grace. And please don't keep it for the last 5 minutes because frankly it might very well fail. Your connection might very well fail in the last 5 minutes. In any case, I'm giving you 10 minutes after the exam to upload anyway. So the 5 minutes is extra. Don't try to keep it till the end of 5 minutes because then it might fail because too many people are trying at the same time. And unfortunately, then you will end up not passing the exam. Okay.
Sir, will it be MCQ?
No, it will be part MCQ, part essay type. It may not be MCQ. I have not set the questions yet, so maybe, may not be. There may be two MCQ questions. The essay type, remember, when I say essay type, I don't mean you have to write pages. All I mean is you have to just work it out, and the working is important. Unlike in the MCQ, where your working could have been just sufficient to convince me that you have actually worked it out. You don't even have to write all the steps. In an essay type question, it really means that you have to actually discuss and show what's going on. Okay, but hopefully okay, not hopefully, I will check that. We should not have very complicated, lengthy things to do, but there may be there may be rather nasty numbers, but you have a calculator, right? All of you have calculators, I hope. So feel free to use the calculators. Or as I said, or the computer. Okay. Any other questions? Anyway, I don't think we need to record this part. It's only going to make the recording longer.